Greetings everyone. Time to show you the final result of the assembly process. Last time I made a video, I had already decided on the module positioning, and now I've completed the assembly. The module positioning was obviously done with RF connectivity in mind, and the main objective is to keep the runs, like the coaxial runs, whether it's semi-rigid, so UT 141, so it's really like copper exterior, some of it is plated, or conformable cable, which I have here coming from the preamplifier. So that's really the critical part. The low frequency part is not as critical, but the 10 gig frequencies, that's the most critical part. But it's a compromise because we have physical boxes such as the power amplifier that has an output that cannot be located right next to the coaxial switch or right next to the feed point. It's not possible. And it's the transmit path, so you're willing to lose a little bit more on the transmit, but you will put your preamplifier close to the feed point, because any loss that's between the feed point and the preamplifier is a deterioration in dB of the noise figure. So you want to keep the losses to the first stage, in this case the LNA, the preamplifier. You want to keep those losses as little as possible. But you have no choice. You need a piece of coax leaving the transition, going to the coaxial switch, which you see right here. It's a single pole double throw. By default, it rests on the receive position, so the LNA gets the signal. When we're going to transmit, this coaxial switch, or coaxial relay if you wish, is operated by the plus 12 volt TX signal coming from the sequencer. And on that switch, I positioned a doubler PCB which produces 24 volts. I've set it to 20. If you recall, in one of the previous videos, I mentioned that it was going to be more than enough, 20 volts for the coaxial relay, because I tried it. So it's an adjustable boost converter with enough current to operate the coaxial relay. I mentioned that I put all the switching supplies on the opposite side, if you recall, in the compartment right behind the dish. Not quite true. There's a little switcher here, but I've added some bulk capacitance, an extra electrolytic capacitor here, to try to filter out excess noise that would go back into the plus 12 volts. So it should be okay. It's a little switcher. It's not very high current either. So receive preamp as close as possible to the feed point. So short run of semi-rigid. The semi-rigid is quite rigid. They call it semi, yeah. You can form it with your hands, but you're not going to do it 20 times. It's going to break. So I used as short as possible of semi-rigid here to the common point, and then switch between receive and transmit. Receive is a conformable cable, not quite as good as semi-rigid, but I had no choice because the PCB inside the LNA, if you recall, it's a recovered LNB. The PCB is so thin and brittle that I could not solder something as rigid as semi-rigid. I had to go with conformable cable, which is a little poorer in terms of losses per foot, for example. But again, it's fractions of dBs, because this is a 3-inch run, 4-inch run. The other one is maybe 5-inch. But the output is not as critical. It's really the input that's critical. But I could not use semi-rigid. So I went for conformable cable, which is still pretty good. It's a microwave cable, but it's just not quite as good. All right, covered on the receive, and then the switch, transmit. The output of the power amplifier gets sent into the switch and then out when we're in transmit, of course. In positioning the modules, I also looked at the available cables that I had. This is a run that I already had. I didn't have to bend it too much, just a little bit to give this curve. But it's the 90-degree bends are natural. They were there on that cable already. And it just worked very well the way it went through here between the semi-rigid and then reached the amplifier input. Everything went really well as far as that goes. Now let's look at the LO chain. Of course, this is 10 megahertz, so any small coaxial cable will do 10 meg into the synthesizer, and the synthesizer produces 3.4 gigahertz. So I have a conformable cable here as well. This one's covered with the heat shrink, but it's the same type as these ones, maybe a little larger. And then out on the 10 gig with another conformable cable, larger diameter, we can clearly see, into the transverter box with a run of coax that is as short as possible. Again, I wish I could put this output right next to it, but you know, you have to deal with this circular shape, and there's only so many priorities that you can set. At a certain point, you have to give in on some of the priorities. Like here, it's a bit of a longer run that I would have wished, but there's enough signal so that the input still is working fine with a bit of additional attenuation. See, it's really compromise. You'll never get a perfect situation. I'd say put your priorities on the receive strip. Make it as short as possible. The transmit, well, it's a big amplifier. You're going to have a longer run, and that's it. For the IF, no real problem. We have plenty of gain, plenty of signal, which we attenuate into this box. So I ran some regular coaxial cable to the transverter. It's the white coaxial cable that we see here, goes here, reaches the little box. Both in receive direction going out to the radio or transmit direction going into the transverter, there's plenty of gain. It's not a deal breaker at all to have a long run. So I've decided to put my box this far away from the transverter. Okay, one other comment that I have is this. On my power amplifier, there's an RF monitor output. Inside, there is a directional coupler with a 30 dB tap. So whatever comes out here, you get 1,000 times less, 30 dB lower signal here. So you can sense the output power, and it's always proportional. So what I did is I designed this little SMA connector. On the back of the SMA connector right here, I put a microwave diode and a capacitor. So it's a sample and hold. It's a diode detector with a microwave diode, and it works fine up to 10 gigahertz. I'm not trying to get an absolute measurement. I want a relative measurement. So since we're always operating in the same more or less frequency of 10.3 gigahertz, this produces a DC voltage that I will be sending onto a movement, a meter movement of 100 microamps. It's a small movement. I've ordered it. I haven't received it yet, but I will be sending this with a current limiting resistor on these to the 100 microamp movement. This produces up to 1 volt when I'm full power, and there's more than enough current to fully deflect the meter. So I'll need to have a potentiometer for a full scale adjustment. So whenever I put out the 3 watts, I'll probably make the deflection go almost to the far right. And then if there's anything going wrong, not getting the full power, the meter will not deflect as much. This is negative voltage that's produced, but of course, my meter movement will be floating, so I can connect it up the way I want and I'll get a positive deflection. I'll have another meter identical to the first one. It's going to be a DC voltmeter to monitor my 12 volts coming into the box. So I'll have 2 meters, power output at 10 gig and DC voltage in. And the meter will give me a rough indication of where my battery sits, if it's dying or anything like that. It's not going to be very accurate, but all I want is get a good feeling that my battery's still up and running fine. Another thing that I've done, I've installed 2 connectors. One for the control, so the signals coming from the FT870, and one for the DC in, the power, the 12 volts. And these connectors are of different diameters. You'll recognize the connector when you see it. See that? It's a microphone, like a CB microphone connector or a ham radio connector of an old type, 4 pins. And this one is a 6-pin, same type but smaller diameter. So no risk of exchanging these two by mistake. So this is how I come in for power and control. For the IF, there's a big hole right here. And if I wish, I can bring out the coaxial cable through this hole, and I'll be able, if I want, to operate with the cover back on. I won't have to leave this compartment open if I do not wish to. So that pretty much covers the layout inside and all the interconnections that I've done. And well, I'm ready to show you how this thing works. In my next video, this is privileged information. I'm going to try to receive a 10 gigahertz beacon that's 120 kilometers away. Stay tuned. 7-3.